Hello everyone. So today we're going to do practice an example on the RLC circuit. This is one of the homework problems that I assigned. So the idea is to calculate the voltages and currents in this circuit after the switch basically changes position at t equal to 0, as you can see. Now I'm going to, as we mentioned, as soon as you have a switch in a circuit, you have to actually break up your analysis into before the switch and after the switch. In other words, you are dealing with two different circuits. I'm going to redraw these circuits, this circuit for before the switch, and move on and do the analysis, and then redraw the circuit after the switch. And this way, I hope this is going to be more clear. Now notice that in this circuit, the switch opens up after t equal to 0, and before the switch the question is explaining that the circuit has been in the status that it is for a long time, and what that means is that everything, all the currents and voltages in the circuit has already settled down. So the current that is passing through the inductor is constant, and the voltage of the capacitor is constant. Now, as you can tell, the capacitor is basically two conductors that are not connected to each other, and if the voltage is constant, there won't be any current, so this behaves like an open circuit. And also you can tell that by through the equation of the capacitor, which says that the current is proportional to the derivative of the voltage, and if the voltage is constant, the derivative of the voltage is 0, and therefore the current is 0. Now, on the other hand, for the inductor, if the current is constant, the voltage is going to be 0, because first of all, this is a piece of wire, and on top of that, the equation tells you that the voltage across the inductor is proportional to the derivative of the current, and if the current is constant, therefore the voltage is going to be 0. Now, when I redraw the circuit before the switch, I'm going to take these two points that I made into account. So let's start. Let's start from the source. So this is the source right here. And the switch is closed, so this is where the switch used to be. Then I'm going to draw the 8 ohm. This is the 8 ohm resistance. Then on one end we get the 70 ohm, and then on the other end here we have the 20 ohm that is in series with the 10 ohm, and the two then get connected to an 11 ohm right here, and then short circuit, which used to be the inductor, and gets connected to the source. So let's put values here. This is the 240 volts, and this is the 8 ohm, this is the 20 ohm, and this is the 10 ohm, and this is the 70 ohm, and finally this is the 11 ohm. So this is the circuit before the switch, and now notice that the capacitor is gone because it's an open circuit, so I don't have to draw it here, and the inductor is gone because it's a short circuit and I don't have to draw it, but the inductor is basically used to be here, and the capacitor used to be connected right here. But by that, what I mean is that they're still there, but we don't show them for the sake of simplicity of the analysis. So we're going to start analyzing the circuit now. We're going to go through the 3-step algorithm. So we're going to identify the nodes. So this whole thing now is one node because everything is short circuited through pieces of wire. So this is all one node. Now what you have here is also one node. and what you have here is another node, what you have here is another node, and finally this is another node. So once we do that, now we start labeling these. So this would be, I'm going to pick that as my ground or 0 volts. Immediately when I do that, since I know what the equation for a source is, it's basically this top potential minus the bottom potential is equal to 240, and therefore this automatically, this node voltage becomes 240 volts. So this I'm going to call V1, and this I'm going to use the same label that was used in the book for the problem. So this is V out, and this would be our V2. Now we're going to label currents. So there's currents for each component. So I'm going to call that I1. There's a current for this component. I'm going to call that I2. There's a current for this component. I'm going to call that I3. And there's a current for this component, and I'm going to call that I4. And at this point we are actually, there is another current here. And by the way, so I can do KCL for this node in my head and just say I3 is equal to I4, but there's no current going there, and that saves me one unknown. So that's actually what I'm going to do. I'm going to go back here and call this I3. Then finally for this one, this is I4. Okay, so now I'm gonna start writing equations. We'll start with KCL and then move on to equations for components. So here KCL. So number of KCL equations that you can write is equal to the number of nodes, basically. But for this node, you don't have to write a KCL. The current that is passing through the power supply is the same current as going out, so this current is the same as that current. And by the way, I could have labeled this one too. For this node, I already did KCL, so, and for the ground, I don't have to do a KCL. Therefore, there's KCL for that node and KCL for this node. So in this node, the currents that are going in is I1, current going out is I2 and I3, and therefore here we write I1 is equal to I2 plus I3. Now for the next node, I2 is going in and I3 is going in and I4 is going out, so therefore I2 plus I3 is equal to I4. So that concludes the KCLs that we need to write. Then we move on for two equations for components. So as we explained, there's an equation for each one of the components in any circuit. We have 1, 2, 3, 4, 5, 6 components here. And the equation for that component, I already used it to conclude that that's 240 volts. So there are 5 equations left. They're all resistors. And the equation that describes the physics of a resistor is basically just the Ohm law. So start from bottom, and the 8 ohm I1 is equal to 240 volts minus V1 divided by 8. For the 70 ohm I2 is equal to V1 minus V2 divided by 70. For the 20 ohm I3 is equal to V1 minus V out divided by 20. For the 10 ohm I3 is equal to V out minus V2 divided by 10. Then finally for the 11 ohm I4 is equal to V2 minus 0 divided by 11. So let's count the number of unknowns that we have in the circuit. We have 1, 2, 3 unknown voltages, and then 1, 2, 3, and 4 unknown currents. So total of 7 unknowns. And then if you count the number of equations that you have, we have 2 KCL and 5 equations for components. So 7 total equations that we have, and this is a solvable set of equations. In other words, now at this point you can calculate all the unknowns. Now, solving a set of equations with 7 equations in it, with hand might be a bit time consuming. Although if you practice, it shouldn't take you more than 5 to 10 minutes to do this at most, even less if you're really good. But then obviously you can use your calculator. If you have a good calculator, you can just punch in all the equations. It's going to spit out all the answers. The other thing that you can do is to just use circuit analysis tricks to simplify this analysis and maybe get to the solution faster. So what do I mean by that? So if you're looking at the current that is coming out of the 240 volts, what you can do is to just look at the equivalent resistance that you see looking into this whole branch, and then if you have one resistance that is equivalent to this and it's connected to a 240 volt, the current that is going to go through it is basically 240 volts divided by that. So you immediately calculate I1 from KCL. Here you can see that I1 and I4 are the same, so you can calculate I1 and I4 basically immediately, and then use a current divider equation to calculate I2 and I3. And as soon as you have all of that, then you can actually calculate all the voltages across each one of these resistors, and you're basically done. So let's use that instead of solving this set of equations to save some time here. So the equivalent resistance is basically this 8 ohm resistance in series with the equivalent of these 2 branches, and then in series with the 11 ohm. So I'm going to call that R equivalent. So R equivalent is basically 8 plus the 70 in parallel with these 2 in series, which is just basically 30, and then plus 11. So now 70 in parallel with 30 ends up being so 21. It's actually 21. So this is 21 ohm. That's 32, and then plus 8, that's 40 ohm. So that's the equivalent resistance here. So as soon as you have that, you know what I1 is, and that would be the total voltage divided by the total resistance. Is just simply the Ohm law, which basically means it's 240 divided by 40. So the current that is passing through is 6 amp. And then from KCL you already know that I1 and I4 are the same, so also I4 is equal to 6 amp. Now the current divider equation would tell you that the 6 amp going in is going to get divided between the 2 inversely proportional with the impedance of each branch, right? So in other words, if I'm looking for I2 would be 30 divided by 100 times 6 amp, the total current that is going in, and so that would be 1.8 amp. And as soon as you have that, the other one is just basically 6 minus 1.8, which is 4.2 amp. So now you have all the currents that are passing through these, and now you can calculate every voltage across. So take basically the equation, in other words, use these equations to calculate any other current that is passing through, any other voltage in the circuit. So for example, now that I know what I1 is, so using this, I just put value of I1 here. So 6 is equal to 240 minus V1 divided by 8. So from that, V1 is basically 240 volts minus 48, and that is 192 volts. Then I know what, for example, here from this, since I know what V1 is and I know what I3 is, I can simply calculate V out. So again, 4.2 amp is equal to V1, which is 192 minus V out divided by 20. So from this, that's 84. So V out would be 192 volts minus 84 volts, and that's simply 108 volts. Now, now that I have the out, and you can calculate all the other voltages if you need to, but at this point, for the sake of analysis of the second stage, which we basically need to open up the switch, all I need to know basically is the initial voltage of the capacitor and the initial current of the inductor. So I already know what the initial current of the inductor is, because this current I4 is the current that is passing through the inductor. This was where the inductor used to be. So the initial current of the inductor, in other words, IL 0 minus is equal to I4, and that's equal to 6 amp. So that's known. And then the voltage of the capacitor is basically this voltage, right? So V out right before the switch is equal to or V out, this 108 volts, which is the voltage across the capacitor. So this is the same as VC right before the switch. Now with that, my analysis is done. I can move on to the next step of the calculation, where now the switch is going to open up. Okay, so let's go to a different page and just remember that these two values are already calculated for us. So I'm gonna rewrite that result here. So IL 0 minus was 6 amp, and V out 0 minus was 108 volts. Okay, with that in mind, now when this switch opens up, something important happens, and that is that you basically don't have any voltage source in the circuit as soon as this opens up, because there is not going to be any current going through this branch anymore, because this is open. And as soon as that happens, you can completely ignore what is going on here. Okay, so this is an important point to notice. And you may think that this opens up and this is still 240 volts. That's not the case, because what we know is that this voltage minus that voltage is 240 volts. And if you don't know what that voltage is, in other words, this is no longer connected to your circuit, this voltage up here is irrelevant. It's not referenced to anything that is actually connected to your circuit. So you have to completely ignore this branch of the circuit. So I'm going to redraw the circuit this time after the switch. And like I said, this branch is gone, so you have a capacitor here, and then you have this branch of the 2 resistor 20 and 70 in series, and then on the other end the 10, and then it gets connected to the 11 ohm and then the inductor, and after that goes back here and gets connected to the capacitor, and that's it. So let's put values. This is your 5 millifarad, this is your 20 ohm, this is your 70 ohm, this is the 10 ohm, the 11 ohm, and finally the 1 Henry. Now this is the equivalent circuit for that, what you see here after the switch. So let's start labeling the circuit again. This whole thing is one node. This is another node. This is another node. This is another node. Right? So let's assume that that's my ground and this is my 0. This is V out t now. Everything is going to be a function of time. This you can call it V1t, and this you can call it V2t. Current's passing. So this is current I. Let's call it ILT. And now I can actually take this and turn it into one resistance and only deal with one current that is passing through. It's just going to simplify all my analysis. What I'm going to lose is that I'm not going to know what that voltage is. But if what I'm looking for is this voltage or the current here or the current here, that voltage is not important for me. So I'm going to just box this up and call it one resistance. And therefore I'm going to just assume there's one current passing through that equivalent resistance, and that's the same as ILT. And the same here. So there's ILT here, and there's ILT here. There's one current in the circuit. I can actually go one step ahead and say that this is also part of that equivalent resistance and redraw this circuit so that we only deal with one capacitor, one resistor, and one inductor, because I don't care about that voltage either, right? So with that in mind, you can keep this circuit the way that I have it right now, but it's easier if you just deal with all of this as one resistance. So let's calculate the value of that resistance before doing anything else. So equivalent resistance would be in that circuit between these two nodes would be the 11 ohm added to 90 ohm in parallel with 10 ohm. Now this is going to be 9 ohm, and plus 11, that would be 20 ohm. So with that in mind, now just imagine that there's one capacitor, one resistor here. If you can't do that, just redraw the circuit. And there's no KCL to write. There's only one current in the circuit. So we're going to directly move on to equations for components. Now, for the resistor, this equivalent resistor, the current that is passing ILT is basically equal to V out T minus V2T divided by the value of the equivalent resistance, the 20 ohm. For the capacitor, ILT, it's called IL, but that's just a name. It's the same current that's passing through the capacitor, is equal to 5 times 10 to the minus 3, which is the value of the capacitance, D. Now, it's going from here to here, so it would be 0 minus V out T. So the minus v out t, I'm going to put that minus sign right there, the v out t dt. And then finally for the inductor, v2t minus 0 is equal to 1 Henry 1 d ILT dt. So these are the three equations. Now let's count the number of unknowns that we have. We have V2, V out, we ignored any other voltage unknown because we turned all of this into one box. And the current that is passing through IL, so 3 unknowns and 3 equations. And this should take care of everything for us. No, I can put this ILT in this equation. So V2t is equal to the derivative of this function basically, which would be minus 5 10 to the minus 3 d2 v out t no respect to dt. So that's v2 as a function of v out. We already know that these two are equal to each other, so I just take these two and replace v2 with this, and I get one equation that is only a function of v out. So I'm taking that, putting this in there, so minus 5 10 to the minus 3 dv out t dt is this equation, is equal to now v out t, so that's, I'm going to keep it, minus v2t. Now I know v2t is this, so that would be plus 5 10 to the minus 3 d2 v out t dt, and the whole thing is divided by 20. So there you go, this equation is only a function of v out. Multiply both sides by 20, so that would be minus 100. Now 100 times 10 to the minus 3, that would be minus 0.1 dv out t dt is equal to v out t plus 5 10 to the minus 3 d2 v out, this is d2 dt2, sorry, d2 v out t dt2. Now I'm going to move stuff around and also divide everything, both sides, by 5 10 to the minus 3, so that I bring this to the general form for the differential equation. So d2 v out t dt plus 0.1 divided by 5 10 to the minus 3 dv out t dt plus 1 over 5 10 to the minus 3 v out t is equal to 0. And that is the differential equation that we have to now solve now. Okay, so let's quickly remember that we had this in our general form differential equation. This was our 2 alpha, and this was our omega 0 to the power of 2. And from this point on, we write this the characteristic equation for this differential equation, and then solve that characteristic equation. It gives us S1 and S2, if you recall, and that was minus alpha plus minus square root of alpha to the power of 2 minus omega 0 to the power of 2. Now let's do this. So 10 to the 3 goes up there, 10 to the 2 divided by 5, so that's 20. So 2 alpha is 20, therefore my alpha is 10. That's good. And this is 10 to the 3 divided by 5, that's 200. So omega 0 to the power of 2 is 200. Okay, that's set. Omega alpha to the power of 2 minus omega 0 to the power of 2 is going to be, which by the way this is sometimes called omega d. So from this, omega d is basically a square root of minus 100. So the solutions to this characteristic equation would be complex and conjugate. So this would be 10j, right? So S1 and S2 are minus 10 plus minus 10j. Now, once that happens, you know that basically what it means is that the solution or the voltages and currents in the circuit are going to be oscillating, and then basically exponentially the amplitude of that oscillation is going to go down with this frequency of this angular frequency that you see right here, and 10 as the angular frequency. So that concludes our solution. You can look up the solution. I can actually write it down right here, maybe down here. I'm going to write it. So okay, so down here, V out T is going to be in this format of B1 e to the minus 10 alpha t cosine of 10t plus B2 e to the minus 10t sine of 10t. So that's the solution for that differential equation. Now we're still not done because we still don't know what B1 and B2 are. So for that I need a little bit more space. Let me see if I can open up some space down here. So at t equal to 0, just you put 0 here. So V out 0 would be, that's 1, and cosine of 0 is 1. Sine of 0 is 0. So this basically becomes B1. Now, if you recall, if you go up here, V out 0 minus was 108 volt, but that's the voltage of a capacitor. So the voltage of a capacitor before and after the switch can't change. In other words, V out 0 minus is the same as V out 0. So down here, this is the same as V out 0 minus that we calculated, and that's 108 volts. So there you go. I know B1. Now with that, I'm going to have to move on to calculating B2, and to do that, I'm going to use the equation for the current of the inductor, which was basically the same current that is going to pass through the capacitor at 0. In other words, IL0 is the same as IL0 minus. The current of the inductor can't change immediately, and that's from this equation that I have right here. Relates that to the voltage of the capacitor, and I have that here. So I'm going to have to take the derivative of this and multiply it by minus 5 10 to the minus 3, and then at t equal to 0, equate that to 6 amp, and I get another equation for B1 and B2. So now, once you do that, the second equation that you're going to get is going to look like this. 10 B2 minus 10 B1 is going to be equal to minus 1200. Now, since you already know what B1 is, 10 B2 is equal to minus 1200 plus 1080, and that's equal to minus 120, and therefore B2 is minus 12. So V out T finally is equal to 108 e to the minus 10t cosine of 10t plus B2, we now know what B2 is, and that's minus 12. So minus 12 e to the minus 10t sine of 10t. So now that we have V out t, you can put that in any of the equations for components that we wrote and calculate any other voltage and current. I'm not going to do that, and hope that has been helpful. Thank you.